Good morning, everyone. Morning. Again, thank you very much for allowing me to speak with you all. I hope I can deliver a good course and good information to you during these few days that I'm going to be with you. Basically, this cover page is the cover page of the book that I recently published with IEEE and John Wiley. And if you look at the title of the book, it's pretty much very similar to the title of the course that we have here. So the plan, as we talked with Dr. Chandrasekharan, was to follow this book for the most part, or the items or the topics from this book. So this book was published about 2 years ago, and I just put the cover page here for your information. So my plan is to go through the contents of the book. It has several chapters. Probably takes a little bit for me to educate myself with this one. All right. So, like I said, there will be 7 chapters in the book on different topics. First chapter is I think I need to deactivate this maybe. It's in the pen mode. So that's the colors, not this one. Scroll using finger. You see? Okay, now it goes. All right. Again, suddenly changes. All right. So, chapter 1 is introduction. Here, you see that. So we're going to talk a little bit about power system and how power system works and what are the challenges we have with power system. So basically prepare the ground for the course and the need for distributed energy resources and renewable energy. So pretty much very general introduction, but geared towards power electronic and renewable energy. Then chapter 2, which is again is general and introductory chapter, it goes into introducing power electronics. So what is really the power electronics? What are the main components of power electronics? What does power electronics do? And what are the applications of the power electronics? So these 2 chapters together is the introduction for the course, and my plan is to cover these 2 for the first class. Most of these 2 chapters. And then this chapter here will be standard power electronic converters. Now we go into details of different converters, a standard buck converter and a standard boost converter. Then, some of the chapters in the textbook also has these asterisks. So for the first reading of the book, I just suggest not to include those chapters. For this course also, my plan is to exclude this for now. Later on, if anybody really wants to discuss those things, we can either do it in the class or separately. But for now, in order to make sure that we can cover as much as possible, I'm going to exclude these things. Then we go into single phase, half bridge, and full bridge converters, voltage source converters. And then here, 3-phase converters as well will be covered. And then we have feedback control system. So by this time, we know power electronics, we know power electronic converters, and then now we go into controls. For controls also what I do, I will give an introduction first. In these topics may be familiar with most of you, for most of you, especially if you have been in control area. But I rather discuss them as well. So there will be one chapter on control systems in Laplace domain or transfer function domain. That's the classic control approach. So we go into details of that. One class will be on control systems in state space domain or time domain. So state feedbacks and optimal control and those things. So one class again on this topic. Now, in this chapter, we really go into introducing what are different distributed energy resources that we have. And the first chapter is a long chapter. It's basically talking about DC distributed energy resources. So we're going to have 3 classes on this chapter, basically, or maybe more, I guess 3. So you will see introducing the problem, solar photovoltaic converters, and the control problems and the approaches here that will be. Should I stay here, maybe? Make it a little larger. Is it good now? So this will be class 5, and then class 6 basically go into further details of the control and especially on the grid support aspects. So this grid support terminologies probably you have heard in different forms, also grid forming converters they're called, so inertia and those type of things. So we are going to cover those things in one class. Then we move to another type of control systems for converters. This is load voltage control. So the previous one was grid connected. This is the case that you are not grid connected. So load voltage control aspects. We will also talk about maximum power point tracking. So especially for the photovoltaic converters connected to the grid. Grid forming converter controllers. So by end of this, we have covered DC, distributed energy resources. Now we have AC. For AC, I broke it down into 2 chapters. One on single phase, that's chapter 6 here. And again, this is a relatively large chapter. I broke it down to 3 classes. So the first one, again, getting to know the problem, the backgrounds and everything, the statement of the problem, and what are the objectives that we are looking for. One new thing that, especially here, we will go into a little bit more detail is the phase lock loop, because when we go to AC systems, we need to also have phase lock loops in grid connected. So there is a separate section here on phase lock loops, harmonics and issues related to harmonics and DC current control. So we go into that. Weak grid conditions is important, but at the same time I excluded in the first course here. If we have time later, we can come back and try to discuss that. Then we have grid supportive controls, and then dynamic support, static support, and virtual synchronous machine, which is one particular type of grid supportive or grid forming controllers. So we go into details of that. The other aspect now is the DC voltage control on the grid connected single phase AC systems. So we deal with that problem here in this class. System modeling and control system designs. And basically we complete that discussion here in class Now the last chapter will be three-phase DERs. So again, I have three classes or more, I guess 3 or 4. So the first one, as usual, will be the statement of the problem, the backgrounds, and those kind of things, and the initial control approaches that are available. So we covered that in the first class. And then vector current control in synchronous reference frame, very common control approach. So we covered that here. We have some innovative things to add in terms of optimal control design. So we will go into details of that as well. Now, grid supportive controls for three-phase. Basically, once you learn the single phase, it will not be very difficult to understand three-phase. Three-phase even sometimes tends to be easier to understand or to operate than single phase. So we go into analyzing those aspects of grid support control, especially again virtual synchronous machine for three-phase. And then we go to DC side voltage control and support here. And finally, we have load voltage control and support. This is basically the cases that now there is a load, we want to control the load voltage. And at the end, we connect these two together, the load voltage control and the grid current control, and we come to grid forming controllers. Okay. So that's basically the content. I don't know if we should give time for questions now or should be at the end. I don't know what is the style for this course. Dr. Chandra is here. Okay. I think it's a good idea to make sure that we cover everything. All right, so introduction. This is about electric power system and the need for change. Most of this will be known by you, but just to reiterate the things that we have about electric power system. We know it's the infrastructure to generate, transmit, and distribute electricity. And it's the largest and most complex man-made system that we have. Electricity, bulk electricity is generated in power plants, and then currently we know it's AC, and is transmitted through the transmission system to the distribution where it is used and consumed. So if you look at this statement that I just said, you can immediately see that power system has three main components: generation, transmission, distribution. So it's a hierarchical system. So generation is basically a power plant that generates bulk electricity. So when we say generate, it's not generation, it's conversion, because energy you do not generate, you convert from one form to another form. So basically the common sources of energy are either fossil fuels, which include coal, natural gas, and petroleum, nuclear reaction, and stored water. And corresponding to this, we have nuclear power plants, or fossil fuel power plants, nuclear power plants, and hydro turbines. Generators are three-phase synchronous generators that generate three-phase 50 hertz or 60 hertz. I think in India it's 50 hertz, isn't it? Yeah. So in North America it's 60 hertz, where I currently am. And then transformers are used immediately to increase the voltage level in order to be able to transmit the power over long distance. Obviously, you all know that we need to increase the voltage level in order to be able to transmit the power over long distance. Otherwise, it's not possible and will be a lot of losses. So that in transmission, basically, we have high voltage overhead lines typically, and transformers are used to boost the voltages. Transmission system is a meshed network to increase reliability, so the power is not transmitted only through one direction, one line. It will be multiple lines that can lead the power to any particular destination. And then at the end of the transmission line, or in anywhere you want to tap the power, there is a transmission substation that decreases the voltage level, and then you transmit further stage, and then you reach a substation which further again decreases the voltage level. So typically we are talking about hundreds of thousands of volts here, and then we're decreasing it to tens of thousands of volts, and finally to a voltage level that you can use. Consumers of the power are either industrial, commercial, or residential users. Residential applications, you are all familiar with it. You every day use it: cooling, heating, lighting, refrigerating, washing, drying, and so on. So if you look at this power system that we just described, is a highly interconnected power system. A lot of generators and transmission lines are connected to really build this huge entity that we call it power grid or power system together. So it's highly interconnected. The reason to build the system this way, the main reason is really high reliability. You want to have the power as much as possible, or without much interruption. So that seems to be the only way of operating a power system like that. So the side effect of this approach will be now maintaining this huge entity, with a lot of generators and loads and transmission lines and everything. And specifically, this is an AC system. In AC system, some aspects become easier and some aspects become harder. So if you look at every generator now oscillating at 50 hertz or 60 hertz, these are connected together. So they need to be synchronized, otherwise this whole system will not operate well. So synchronization of this entire power system is an important aspect. We go into details of this synchronization from the perspective of power electronic converters in much details later in the subsequent lectures. So maintenance of this system. Power outages all the time happening for many different reasons, and maintaining this system, synchronization of this system, control, protection of this system against faults and overcurrents. These are everyday challenges that we have in the power system. So as far as technical. Now, this is another challenge here that we have that kind of connects us. This also would do, but this even more connect us to what we want to say. If you look at the information from US Energy Information Administration, for instance, for 2016, that's the time I was writing this document, but later I updated a little bit more. But the data are there for even maybe 2024, the data is being updated all the time. So it says in 2016, 4.1 into 10 to the power of 12 kilowatt hour of electricity was generated in the US. The amount of CO2 emission was 1.821 into 10 to the power of 12 kilogram. So if you just do a simple calculation, you realize about 0.44 kilogram of CO2 emission is generated per every kilowatt hour of electricity on average in 2016 in the US. So these are the information about that system. Now just imagine an average house in US consumes 900 kilowatt hour of energy per month, and then do the multiplication, you will realize that about 400 kilogram of CO2 is generated by every individual house per month. And then we are talking about 4.8 tons of CO2 per year generated by just one house. So this is a huge problem that we have, and that's basically what everybody is concerned about in terms of pollution that, or the price that we are paying to have a cheap, reliable power grid. It's a magnificent, I would say, achievement that we are using it every day, but it looks like we are paying a very high price for that without paying probably adequate attention to it. So this will, and CO2 emission, impacts on the nature, greenhouse effect, these are the aspects that we have here. So this is not sustainable approach because the need for energy is ever increasing, and if you want to continue with this approach, it's not going to work for long term, in long run. A few other aspects that we are here, we can talk about. These approaches that we currently have for generating electricity in the big power plants, we said, based on fossil fuels, or nuclear or hydro. If you look at the efficiency of the power plant, typically ranges from 30% to 40%. So in the best power plants, like very sophisticated, modern natural gas power plants, we can reach 40%. Right. So that is also one major aspect of this power system. Transmission losses due to the nature of this power system, that power has to travel from generation to the distribution, and generations we need often to build them far away from consumer sites because of, again, of the pollutions or because of the resources that are available at that site, not where we want to use. So transmission losses about 5 to 10%. So 5 to 10% of the power that we generate will be lost before reaching the destination. And we already alluded to the fact that if you have a large power system, maintenance of this power system is also very costly in terms of operating, making sure that the faults and outages and blackouts and all these things are addressed in a timely manner. Okay, so this really summarizes some of the aspects or challenges that we have in power system. What is a potential solution, again related to what we would like to talk in this course, is using renewable generation. So renewable energy is an energy that is renewed naturally in a human time scale. So, because if you don't consider really this definition, everything is renewable. Even fossil fuel is renewable because it's generated by nature, right? But it's not generated in a human scale. So if you use it, then you have to wait hundreds of thousands of years again for the nature to generate that. So the energy coming from solar is a renewable because it's all the time the sun is giving us energy. So if we can harvest that energy, it's no problem. Energy in the wind or in the moving or stored water, we consider all of this as renewable energy. And then if you have distributed or dispersed generators that they can generate electricity from these resources, not in a huge power plants, but in a smaller generation facilities. So, and then you can use that power closer to where you generate them. Then you can also minimize the distribution. First of all, losses, and also the investment that you have for. Because you remember, transmission system, first of all, the losses is very important, but transmission system is also very expensive. Probably the most expensive part of the power system is the transmission part. Okay, so distributed energy resources based on renewable energy. That seems to be a very promising solution to address almost all the challenges that we just said. But yeah, saying it is very easy. We'll see the problems that we will have. But before going to problems also, let me give you some examples. The term distributed energy system or distributed generation, basically keep in mind it doesn't mean necessarily renewable, so it could be renewable or non-renewable. Distributed or dispersed means it's small and it's distributed across the distribution system. Okay, so solar photovoltaic, solar thermal, wind, tidal, and microhydro. These are some examples of renewable distributed generation. And for non-renewable, we have microturbines, diesel generators, for instance. Geothermals, we also consider them as renewable, that they are available in some locations, that we can tap to the heat inside the surface of the earth. Biomass generators, that they burn biological materials from nature. Again, we can consider that as, yeah. Fuel cell technology uses chemical reactions to generate electricity. That is also another technology that we can consider as renewable, even though the terminology differs from PV to fuel cell, so not exactly the same, but still we can consider that. So additional benefits of deploying distributed generation: reducing transmission losses, we already talked about that, and deferring or reducing the transmission system expansions, and recovering the heat loss. Because if you are generating close to the consumer side, you can also use the heat generated. If it's non-renewable, let's say it's a diesel generator or a microturbine, then you can recover the heat as well to heat the water at the residence, for instance. Okay, so I will provide these documents to you, so later you can read, especially there are a lot of details in the footnotes, so feel free to read those numbers and details. And participation of consumers in market. Now, if it's distributed generation or dispersed generation, that means they are freely owned by the people, so they can generate and then participate in the power market. Then another aspect is, if we are generating in the distribution, at the distribution level, we are not necessarily dependent on the transmission system, whether the transmission system is there or is not there. Let's say it is there. So we are not dependent necessarily. So if we have sufficient amount of generation at a distribution system, we can disconnect this distribution system from the transmission system. That is the concept of autonomous or islanded operation of a section of distribution system. These distributed systems can provide ancillary services to the grid. So there are many different types of services, we call them ancillary services. They can provide to the grid, and they can be reimbursed for that. Keeping the oil and gas prices more stable and lower for longer times, and lowering the dependence of power industry on oil and gas industry changes and uncertainties, because this is an industry which has always been very uncertain and dynamic. Okay, so what are the challenges with this approach? Well, first, keep in mind that our assumption here is that we have a power system is operating. So these challenges, basically, most of them are related to that aspect. So we have a power system which is working currently, but we would like to mitigate or reduce the problems that it has, right? So basically, if you look at this power system, we said the power flow is unidirectional from generation to the distribution through the transmission. And then maintaining and operating this power system will necessitate putting a lot of, for instance, breakers, switches, and relays to protect the power system. And especially these devices are crucial for the power system. We cannot really operate a power system without these devices. Anytime a fault happens in a corner of power system, now these protection devices come into the circuit or operate and isolate that portion of the power system from the others, so the fault can be addressed and then reconnect back to the power grid. Now those devices basically are, if you look at into how they operate, those relays, for instance, or basically, or circuit breakers. These are the typical like fuses that we have in the smaller circuits, but in power system. So they largely operate based on the voltage profile across the power system. Right? So now, if you are, so for a power system that the power flows downstream from generation through this transmission, this voltage profile is used to design or to locate, first of all, this equipment, and second, to design the thresholds for those devices to operate, so protection relays. Now, if you start connecting distributed generations in different points of the distribution system, this voltage profile will change. Now you need to rearrange again the protection systems. So that's the first item that I have here. So the bidirectional power flow. Bidirectional means now the power can also flow back. At a given node, it can flow back to the power grid. We can substantially change the voltage profile. This will cause malfunctioning of voltage regulating devices, especially voltage regulators that are in the substations. And capacitor banks also that are used for, we use this as well. So we have capacitor banks and voltage regulators. The second item particularly is regarding the protection. So the system's response to faults. When the faults happen in the system, again, these protection devices mostly are based on detection of an overcurrent. So when the fault happens, fault normally is a short circuit fault. So one line of the system connects to the ground, or two lines connected together. So a huge amount of current will flow, and the protection device detects. So those devices are designed to detect this flow of current and take action. Now, if you have generators now inside the distribution system, it will actually interfere with the operation of these devices. So relays and other protection devices. Another aspect 3 here, is grid stability problems. What do we mean here? What grid stability problems? Again, just look at, for instance, AC is easier to see it. It's AC power system. Solar rays that are radiating to these panels. And we know that even if you have a completely sunny day, it actually starts at some point in the morning, goes to a peak, and then comes back to zero in the late afternoon. So we have this change. But apart from this change that happens during the day, we have also changes that are completely uncertain and stochastic. If we have a cloudy day, that clouds are moving back and forth. So we have variable nature of variable energy generated, uncertain and variable. These two terms, uncertainty and variability, basically characterize the nature of energy that comes from renewable sources, and basically we are talking about solar and wind at this time. These are two main sources of renewable energy that we have. So both of them are uncertain and variable. So one approach to address some of these aspects is to use grid-scale battery energy storage system. Obviously, if we can store energy, we can use it back whenever we need it. Which has attracted a lot of people in the past decade, especially, and a lot of utilities are trying to use larger and larger batteries to store energy. Yes, if you can if you can store energy and can use it later whenever you need, you can address a lot of these problems. But remember, what was the original problem? We are not kind of solving that original problem, because batteries are not, first of all, these are devices which are very expensive with the current technology that we have. These are not technologies which are nature friendly, and these are not just energies that can recycle, for instance, easily. So battery is not really a solution. It should be there. It looks like it should be there to be used and optimized, but it's not something that can be freely used at any large scale. Right? Okay. Did this one more time? Okay. All right. So oil landing prevention. This is also one challenge that we have with distributed generation, because on one side, on the one hand, we said we would like to have that facility that, if needed, we would like to island one part of the distribution system, if we really need it and it is under control. But on the other hand, there is a side effect to that this islanding should be completely under your control and under your knowledge. In other words, you don't want to have an island when you don't want it, because it's dangerous. Right? Let's say the part of the power system is going through a problem, and then in the conventional power system, when you have unidirectional, the protection device opens, or you open that part of circuit, and then you go there and fix the problem. Right? But now, let's say even that switch opens this part of the distribution system, which is under fault, parts of that, and then you want to fix the problem. So you don't want some of these generators to keep powering the distribution system. So for the sake of safety of the people who are working on that part. And last but not the least is coordination and control of this many number of distributed generators. So how you would like to coordinate and control them, because now the number can grow really to very large numbers if everybody wants to have a generator on top of your roof as a solar photovoltaic or small wind turbines or things like that. So this also can become very challenging. So these are all technical aspects. Then obviously there are regulatory and policy related challenges, which is not my job, and I think probably most of you. But these are other aspects that utilities and governments and those need to take care of from those aspects. Now, these challenges, keep them in mind. Now I'm going to microgrid. Microgrid basically came out of these challenges. And especially the last few that I saw, this control and coordination, also protection. So the idea is, okay, now let's not go all the way from this standard power grid now to a completely open. Let's go to a midway, and then now we cluster a number of generators and loads and everything together to build an entity, and we call that a microgrid. And that entity is connected to the rest of the network at one single point. So now you can look at this cluster of generators and loads as one entity and deal with that as one entity. That is a microgrid. So a microgrid is a cluster of distributed energy resources and loads that is connected to the grid at a single location. It can operate in grid connected and islanded, so at that particular point can be disconnected from the power grid or can be connected. Okay. So what will be the properties of such a concept? If you have a microgrid, then when it is connected to the power grid, again, it's a larger, you can say, compared to one single distributed energy resource, is a larger entity. But it interacts with the grid, again, at one single point. So at that one single point can exchange power with the utility. So reactive power or real power. It can provide services to the power grid. It can do fault right through and grid support. So these things will go into detail in the future classes, and can also even provide stability support and improvement to the power grid. And power quality aspects of this entity should also be studied in terms of harmonics, unbalance, flickers, and so on. And when it is disconnected from the power grid, basically, if it needs to operate as an autonomous system, so the voltage quality across this microgrid terminals or points or nodes is very important, and power management and power sharing within the microgrid of the generating units inside it. It should be able, ideally, to operate in both modes, grid connected and islanded mode, and should be able to transition from one mode to another mode without difficulty. Now, if you look at these properties, if we can manage to have these properties, these are very nice properties, right? And then it will solve a lot of problems that we were just talked about in terms of managing distributed energy resources. So this is an introductory chapter, so a little bit sometimes disjoint. For instance, now here I'm talking about inertia. This is another aspect that we have in power system. Kinetic inertia of synchronous generators is, you all know, most likely, that has been very important in maintaining the stability of the power system. So that's the inertia, that the power which is stored in these rotating masses that are inside the generators. And again, later on in one of those chapters, we go into the mathematics of how the inertia works and those things. But now just showing it. Okay, so this whole power system is really very much dependent on this inertia in terms of operation, stability, and even synchronization. So it's very important. When you want now to integrate more and more of distributed generation, like solar, photovoltaic, and even wind, even though it's a rotating mass, it has a rotor at the generator side, but we never connect, almost never, directly wind turbine to the power grid. So it goes through power electronics. So again, the kinetic energy is lost somewhere in between during this process. So A power grid based on a huge amount of distributed energy resources will not have that kinetic energy or that inertia. That's one aspect which is kind of concerning, has been concerning for a lot of researchers in this area. Okay. So we alluded already to the topic of storage. Storage is not necessarily only battery energy storage. We have different types of storage discussed here, so you can read that. So here this diagram, if I want to explain a little bit, we have in every distributed energy resource, we have a primary side here. And then we have a power electronic converter, and then rest of the network. And then let's say all of them together generates or constitute a microgrid for us, which is connected to the grid at this point. And this is a local area grid, and then another switch here connected to the larger power grid. Okay. Two, about anti-islanding, you can see. All right. All right. Sure. So we'll have about 10 minutes. 10, okay. It's all right. Sometimes first few lectures will be a little slow just to get to the flow, but we continue. So, okay. So primary side, talked about that. It could be any type of energy resource. By the way, DER, when we say distributed energy resource, it's not necessarily generator. It can be even a storage or consumer. It is an entity that's technically, it means you have controllable interaction with the power grid in terms of either generation or consumption or storage, which is both way. Power electronic converter, basically the two jobs that power electronic converter does is converts or shapes the power, and it controls it. So these are the two jobs that power electronic converter does. So shape of the power, DC, AC, single phase, three phase, these type of things, and then controlling the amount of power, flow of power. Okay, I think that was it for this chapter. Let me see what else I have in this chapter. And these are the secondary aspects of jobs of power electronic converter. power quality aspect. So if it's connecting one resource to the power grid, so make sure the power quality aspects that the power grid requires are satisfied. Ancillary services, these are again secondary jobs. Reactive power support and so on. Okay, so we go into details of that fault right through in details later. We don't need to discuss now too much. So some common topologies that we have, this is like we have a DC input, let's say a solar generator, then you have DC to AC, and this is switches that really what they do, they chop, so to speak, they chop the voltage and generate an AC from DC, but that voltage is not smooth, so you need a filter to make that voltage or that current smooth. So this is called a single stage. You directly convert DC to AC. Then you have multiple stage, like two stage here. So DC or AC, you convert it to DC, and then now you have DC to AC. So this is used again in solar, in battery, and especially in the wind application, you need to use double stage. Multi-stage are also there, but basically single stage and double stage are the most common that we have. Okay. So this is chapter 1. Let me start chapter 2. We will not be able to finish in the first class, but we'll do it in the next class. Okay, power electronics. So this chapter basically is going to give you an introduction of what is power electronics, what is a power electronic converter, and what it does, how it does its job, and then what are the applications in a very brief way without going into too much details. So a power electronic converter, also some people would like to call it a power processor, uses power electronic switches such as diodes, power diodes, and different types of power transistors combined with passive circuit components, and basically we mean by that inductors and capacitors, to convert, again the job of this converter, to convert one form of electricity to another form and to control the flow of that power. So when we say one form to another form, you can say DC to AC, AC to DC, or even DC to DC from one level to another level, or changing frequency, phase angle, magnitude of an AC, or changing from single phase to three phase. These are all conversions of form, right? And then the second aspect, I said, control of the flow of power. It can be unidirectional from one side to another side, or bidirectional. Okay. The way that it does this job, a power electronic converter, is by fast switching, turning on and off, we call it switching, of a device. This is called power switch. So the switches that we have, so this diagram, I'm sorry, I have to learn a little bit how to go forward. So this diagram shows what power electronic does. It basically, it is interface between two sides, let's say side A and side B. I didn't specify what is side A and what is side B to keep it general. And then there is a controller here that controls or specifies the times of each switch inside that converter to turn on and off. So by turning on and off of the switches inside this converter, the interface between these two will be established, and that interface, like I said again, it has to basically do two main jobs: conversion of the form and control of the flow. So, for example, side A could be solar panel and side B could be power grid and different things. So, power electronic switch is a semiconductor device that can permit and or interrupt the flow of current by the application of a gating or activating or switching. The same thing but different names. Signal. So by just one signal you can turn on or turn off that switch and then let the current flow or interrupt the current. Diode is an exception in the sense that it does not have a gating. Advantages of power electronics, basically fast dynamics, there is no mechanical part engaged. They have good controllability, just by one signal you can control, and then smaller footprint again compared to the mechanical switches. So diode, you all are familiar with diode. This is the characteristics, current voltage characteristics. A more realistic diode basically has a conducting resistor and also a voltage drop across the diode when it's turned on. So it can only flow the current flowing from anode to cathode, and it can block and it will block the current flowing the other way. Like I said, that's the only switch that does not have a gating. Thyristor or SCR, silicon control rectifier, can only be turned on using its gate signal. So you cannot turn off this using the gate, SCR. One of the oldest technologies that we have, very powerful for large amount of current to flow. The limitation is, first of all, it cannot operate at very high switching frequencies, typically around 1 kilohertz or slightly above 1 kilohertz. That's but it can handle a lot of current. Gate turn off, GTO, basically has the same properties of SCR, but with the difference that now if you can pull a current out from the gate, you can turn the device off as well. In other words, it has addressed the turn off weakness of the thyristor. IGCT is a GTO in terms of a structure, but that limitation of GTO, which is large amount of negative current at the gate, has been addressed. And also the switching frequency is higher and the lower on-state voltage drop compared to the GTO. The most common one among the switches that we have currently is IGBT, insulated gate bipolar transistor, fully controllable, turn on and off, relatively high switching frequencies in up to, I think in the good IGBTs, high frequency, we can approach close to 100 kilohertz. And it can handle a still rather large power. Not as much as SCR, but still rather large power. MOSFETs, power MOSFETs can really improve in terms of switching frequency and efficiency. They have lower losses, but the limitation they have compared to IGBT is the level of the current and voltage that they can handle. By the way, the level of current and the voltage with the switch, the current is clear, is the amount of current that it can tolerate when it is on, the maximum amount of current, or the rated, yeah. Because it's the difference between the maximum and the rated again. So rated is the typical, yeah, but the maximum is slightly above the rated. So that's the current. For the voltage, because when it is on, there is only a small voltage across that, but it's when it is off, how much is the maximum voltage that it can tolerate. So power does not really mean a lot in a power electronic switch. But some people would like to multiply these two entities, this voltage, into that current, which is not really scientific, because one of them is for the on state, one of them is for the off state. And they call it the power rating of the switch. All right, so I think as far as switches, let me talk about just 1 minute about IPM. Intelligent power modules are very common nowadays. People no longer really build normally individual switches. Now you can buy multiple switches connected together. So, and you will see, because in converters we hardly use one switch. Most of the converters that we have multiple switches, 2, 4, 6. So why not buy all of them together? And all the circuitry and protection around them. So it's called a power module or intelligent power module. These are the circuit diagrams for these switches that I said, power rating thing. And the last thing here is wide band gap devices are becoming now very attractive. These are the devices that can switch much faster than silicon switches. These are either silicon carbide or gallium nitride. These are the two common ones that we have currently. And they can go really, really high switching. And depending on how much power and voltage, again, they can handle, that goes down. There is a trade-off always between this rate of switching and the power that they can handle. But they can switch really very high, up to megahertz, 1 megahertz, 2 megahertz even, some of them. So these are some of the new technologies. So I will continue in the next class.